Hi, today I'm going to talk about the complexity of promise constraint satisfaction problems, which is joint work with Stanislav. Živný. I'll first talk briefly about the constraint satisfaction problem, of which promise constraint satisfaction problems are a generalization. Suppose you have a graph, as on the left here, and you want to know whether it has a 3 coloring. This can be framed equivalently as a graph homomorphism problem. Does an input graph have a homomorphism to the complete graph K3 on the right? A homomorphism in the context of graphs means that each edge of the input graph is preserved in the output graph when vertices are mapped to vertices. And the notation we use for this is CSP of the target structure of the homomorphism. The promise constraint satisfaction problem, or PCSP, is a generalization of the CSP that enlarges the gap between yes and no instances. Consider, for example, our graph coloring problem from before. Instead of asking now whether our graph is 3 colorable, we ask instead, is it 3 colorable or is it not even 5 colorable? In terms of homomorphisms, these questions are equivalent to, does our graph have a homomorphism to the 3 clique or no homomorphism to the 5 clique? Intuitively, this problem could be easier than the 3 coloring problem, because we'd expect graphs that are 3 colorable to look quite different from those that are not even 5 colorable. We could enlarge the gap even further to now 3 colorability versus 12 colorability, and we'd expect, again, the graphs that are 3 colorable to look quite different from those that are not even 12 colorable. The notation we use for these problems is as follows: PCSP of the first structure, comma the second. In this case, PCSP of K3, comma K5, and we call K3, comma K5 the promise template. It is conjectured that all problems of this form are NP-hard, which means that knowing that a graph is 3 colorable doesn't help you find a 3 coloring or a coloring with any fixed number of colors. Now we define the PCSP more generally. So for an input C, we want to distinguish between the two cases, that C has a homomorphism to A and C has no homomorphism to B. Let's compare this to the context of graphs, where C was our input graph, A was the triangle representing 3 coloring, and B was, for example, the 12 clique representing 12 coloring. In this case, in the decision problem, the promise is that we never have C not mapping to A, but C mapping to B, which means that in this example, we don't have that C is not 3 colorable, but is 12 colorable, which enforces the gap between the two cases. There's also a search version of this problem, which is as follows. If we're guaranteed that there exists a homomorphism from C to A, but we don't know what it is, does this make it any easier to find a homomorphism from C to B? In this case, the promise is that C maps homomorphically to A. To see that this is indeed a generalization of CSPs, note that PCSP of A, comma A is just CSP of A with no gap in between. The main problems we'll look at in this talk are those related to hypergraph 2 colorings. For 3 uniform hypergraphs with 3 vertices in each hyperedge, one such type of coloring is the 1 in 3 coloring, which has exactly 1 color of color 1 assigned to each vertex, with the other 2 colors being 0. Another coloring is the not all equal, or NAE coloring, which accepts all 3 tuples except those where all the vertices have the same color. These are both classic NP-hard problems as CSPs. But now we can ask, can we combine these to create some promise version of hypergraph coloring? What would this look like? Well, we would have an input hypergraph H, and we would want to distinguish between the cases where H has a 1 in 3 coloring and H has no NAE coloring. In fact, it turns out that this problem is tractable, even though both CSPs on their own are NP-hard, as was shown in 2018. And importantly, we note that every 1 in 3 coloring is an NAE coloring, which makes the template 1 and 3, NAE a valid promise template. Now that we know the complexity of PCSP 1 and 3 NAE, we can consider generalizations of this problem. One such generalization is to larger arity, K, where we get problems of the form PCSP T and K, NAE. A tuple is in T and K if and only if exactly T of its entries are equal to 1. For the same reasons as PCSP 1 and 3 NAE, this new problem remains tractable for all K at least 3. Another generalization is to add tuples to the first template or remove them from the second template to narrow the gap between the two templates and thus potentially make the problem harder. In the first case, we add a set of tuples S to T and K, and in the second case, we remove a set of tuples S from NAE. The following illustration tells us why we should expect there to be more hardness. PCSP from T and K to NAE is tractable by the first bullet point here, and PCSP from NAE to NAE is NP hard, since it's just CSP of NAE. So as we move a template along this interval, we would expect there to be a transition from tractability to hardness. Similarly, PCSP of T and K to NAE is tractable, and PCSP of T and K to T and K is NP hard. So we would again expect there to be a transition from tractability to hardness, depending on where our template falls on the interval. These are non-symmetric Boolean PCSPs, since the sets S don't have to contain tuples of every Hamming weight. So the most powerful result for Boolean PCSPs, the Boolean symmetric dichotomy, does not apply. We show that for essentially all the PCSPs obtained via these interval constructions, we get hardness in some sense. Our first result is that when adding tuples to T and K, we get PCSPs that are not solved by the strongest PCSP algorithm known, called BLP plus AIP, unless the PCSP satisfies some parity constraint and is tractable for some simple reason. Our second result is even stronger and gives NP hardness for PCSPs obtained by removing a set of tuples from NAE, unless, again, a parity constraint is satisfied and the PCSP is tractable for a simple reason. The proofs of these two results rely heavily on polymorphisms, and we'll spend the rest of the presentation outlining the proofs. Polymorphisms combine PCSP solutions into new ones and characterize the high-dimensional symmetries of the PCSP solution space. To illustrate the concept, we'll give some examples of polymorphisms of the template 1 and 4 NAE, which from before we know to be a tractable template. The XOR function of arity 5 is a polymorphism of this template. This function takes the sum of its inputs and returns the value mod 2. A function is a polymorphism whenever we take columns from the first template and apply the function to each row. We obtain an output that's a member of the second template. In the case of XOR 5, we can check that the following example works. Each of the columns contains exactly 1, 1 out of its 4 entries, so is a 1 and 4 tuple. And now we check what happens when we apply XOR 5 to each row. The first two rows have a single 1 in them, so the output is 1. The third row has 2 1s, so the output is 0, and the fourth row has a single 1, so the output is 1. And indeed, our output tuple is an NAE tuple. The alternating threshold function of arity 5 is also a polymorphism of this template. This function takes the alternating sum of its inputs and returns 1 if the sum is larger than 0. Again, we can check with the same set of inputs that the function works. In the first row, we have a 1, but it's on an even coordinate, so it'll appear negated in the sum, giving an alternating sum of -1. And so our indicator returns 0. Similarly, in the second row, we have a 1 in the second coordinate, so our function will return 0. In the third row, we have a 1 on the first and fifth coordinate, giving an alternating sum of 2, and we get a 1 as output. And in the last row, we have a 1 on an odd coordinate again, giving an alternating sum of 1. And again, our output tuple is an NAE tuple. It turns out that the template 1 and 4 NAE has XOR and AT polymorphisms of all odd arities, from which it derives its tractability. Polymorphisms are important to the study of PCSPs because the identities they satisfy completely capture the complexity of a PCSP. In general, if a problem's polymorphisms satisfy many identities, we get tractability. And if the polymorphisms satisfy few identities, we get hardness. Most of the work on PCSPs so far has been trying to determine which specific identities are necessary for tractability and which for hardness. An example of such an identity is two-block symmetry. We say that a function f is two-block symmetric if its coordinates can be partitioned into two blocks, such that f is invariant under permutations within each block. An example of a two-block symmetric function is the AT function from the previous slide. We can permute the values on the even coordinates or odd coordinates among themselves without changing the output of the function. Any symmetric function is also two-block symmetric, such as XOR from the previous slide. This happens since symmetric functions are invariant under all coordinate permutations. The proof of theorem 1, in fact, relies heavily on the two-block symmetry identity. First, to recall the theorem, PCSP of T and K plus some set of tuples S, NAE is not solved by the strongest PCSP algorithm unless the parameters satisfy some parity constraint, in which case the problem is tractable for simple reasons. The connection to two-block symmetry is the following theorem. PCSP of AB is solvable by BLP plus AIP algorithm if and only if the template AB has two block symmetric polymorphisms of all odd arities. Therefore, the main challenge is to show that templates of the form T and K union S, NAE don't have block symmetric polymorphisms of all odd arities. How do we show the absence of two block symmetric polymorphisms? First, note that it suffices to show the absence for templates of the form T and K plus a single tuple X, NAE. This is because these templates have the largest gap between the first and the second relation, and so hardness of the others will follow via reduction. Next, every two-block symmetric function can be represented as a function of the weight on one block and the weight of the other block. In this case, we call the two blocks the odd and even coordinates. If the odd block has size L plus 1, then its possible weights are from 0 to L plus 1. And then the even block of size L has weights possible from 0 to L. We would like to construct inputs so that within each block, every row has the same weight. The reason for this is as follows. If here, the block on the left-hand side, we achieve weight W1 in each row, and then in the second block, we achieve weight W2 in each row, then our function f will be forced to return the same value on each row, thus violating the NAE relation and preventing f from being a polymorphism. Note that it does not matter what the exact set of zeros and ones looks like within each block, as long as the weight constraints are satisfied. We must construct blocks with row weights W1 and W2, as in the diagram on the previous slide. One idea to accomplish this is to take cyclic shifts of the T and K tuple. Every row in this case will have weight T. For example, in the case 2 and 5, we get the following cyclic shift matrix. We take the tuple of 2 ones followed by 3 zeros and shift it down one row at a time until the matrix is filled. This completes the case W1. But now, how do we take W2? We cannot simply take the same matrix again, because then we'll have an even number of columns in total, and two block symmetric functions must have odd arity. In particular, the size of the two blocks must differ by 1 to achieve arity 2L plus 1. The choice of W2 turns out to be much more difficult, and it may need to take multiple values depending on the parameters of the problem. For example, in 7 and 15 plus the special tuple of weight 10, we need W2 to take value either 7 or 8, and we obtain the following block. In the first few columns, we have our special tuple of weight 10, and then in the remaining columns to the right, we have 7 and 15 tuples with their ones distributed in a special way. The ones are distributed so that the weight on each row is either 7 or 8. And note that in the top set of rows, there is additional weight from our first few columns, whereas in the bottom set of the rows, we must compensate for this by placing more of the ones. These matrices are typical of those in the proofs of the general case. This concludes the proof of Theorem 1. We now turn to the proof of Theorem 2. First, we restate the theorem. PCSP T and K, NAE minus S is NP hard, unless the problem's parameters satisfy some parity constraint. If the parity constraint is satisfied, then all tractable cases have two block symmetric polymorphisms or reduced to tractable CSPs. Otherwise, we are in the hardness case, and hardness is proved by reducing our PCSPs to symmetric PCSPs using a symmetrization trick, and then applying the symmetric Boolean dichotomy. The symmetrization trick suggests that in the template AB, the symmetry of A is more important in a sense than that of B. We have the following proposition. If A is symmetric, then so is its homomorphic image, which leads to the symmetrization trick. Let A be a promised template with A symmetric. Let B prime be the largest symmetric relation contained in B. Then we can freely interchange B and B prime without changing the complexity of the PCSP. This is useful in our problem because the template A is equal to T and K, which is symmetric, and the template B is equal to NAE minus S, which is not necessarily symmetric. However, this tells us that we can ignore the non-symmetry of the second template and replace it with a symmetric template. We can then apply the following result, which is the symmetric Boolean dichotomy for PCSPs. This says that if your PCSP does not have any constant and, or, XOR, alternating threshold, or threshold polymorphism families, then the PCSP is NP hard. We show for our family of problems that none of these polymorphism families exist. The proof is not very deep, and the main challenge is ensuring that all the cases are covered. We conclude by mentioning a few open problems. For PCSPs of the form T and K union S, NAE, we have shown that they are not solved by the currently strongest known algorithm for PCSPs, but we have not managed to show NP hardness, so this could be a next goal. We can show NP hardness in the case 1 and 3, but our arguments do not generalize to higher arity. Next, we could also investigate the complexity of PCSPs whose second template is NAE, or whose first template is T and K, over non-Boolean domains. Already, our arguments generalize to show that taking NAE over a non-Boolean domain, we still do not get a PCSP that is solvable by BLP plus AIP. Thank you.